Okay, so our task is to determine whether this series written over here on the left, whether this series, too big of a pen there, whether the series converges for all real numbers x. So just a quick recap of what it means for a series to converge. If we have this series 1 plus 1 over 2 plus 1 over 3 plus all the way to 1 over n, as n goes to infinity, this series would converge, okay, as n goes to infinity. And the reason is because you're adding smaller and smaller values. 1 over n, think about like as n goes to infinity, think about how big the denominator is getting while the numerator just stays the same at 1. Okay, you've got 1 over 1,000, you've got 1 over 100,000, and if you plug those numbers into your calculator, you see they get closer and closer to 0. So it's going to converge. We haven't said exactly what number it's going to converge to. Could be like 4, could be like 3, could be 3.5, but we can use tests to at least tell us whether it's going to converge or diverge. Okay, so that's what a convergent sequence looks like. So we can use, and this video is going to cover the ratio test, which is written over here in the top right side. The ratio test works by taking the limit as n goes to infinity for the next term in the sequence, the a sub n plus 1th term, divided by the a sub n term. So there's that ratio of the next term to the current term. And if that ratio, we call it r, whatever that ratio is, if that ratio is less than 1, then we say the series converges. Okay? If it equals 1, then we can't tell, but if it's greater than 1, then it diverges. So what you're going to see is there's often times where it will converge for certain values of x up here. Okay? And sometimes it doesn't matter. Sometimes it will converge for all values of x. So let's check out this series using the ratio test. So what we're going to do is we're going to take, I guess before we begin, just to be clear, this is a sub n, right? This is the sequence that we're summing from n equals 1 to infinity. This is our a sub n. So let's start using the ratio test. We're evaluating the limit as n goes to infinity for the absolute value of e to the n plus 1th power, because remember I'm doing the next term of the sequence first. And it's x to the n plus 1 power over n plus 1 factorial. And I'm going to write it with division, okay? Because if you have one thing divided by another, you could write it in fraction form like this, but if we can avoid it, it's nice to avoid those double-decker fractions, right? So we're dividing that by e to the nth times x to the nth power over n factorial. Okay, so let's expand that limit a bit more. Actually, let's check out what we got here. We got two fractions that are being divided, so we probably saw this in a previous math course where, if we got a lot of complicated algebra, we can still do fractions the same old way that we were taught. If you divide fractions, you can flip and multiply the second one. So that's what it looks like when we flip and multiply the second fraction. And now that we've done that, oops, as n goes to infinity. Now we're going to see some terms cross cancel, okay? But just to be clear, let me write out what this numerator is going to look like. E to the n plus 1, that's the same thing as e to the n times e to the first. And I'll show you why. X to the n plus 1, that's the same thing as x to the nth times x to the first. That's over, actually, let's pause there. The reason why we're able to say e to the n plus 1 is e to the n times e to the first. Remember, that's x to the a times x to the b back in algebra. If the bases are the same, then you can add the exponents, when you're multiplying them. So I just applied that rule over here. And then just a quick reminder of factorials. If you have, let's say 7 factorial, that's 7 times 6 times 5 all the way down to 1, okay? Or you could say it's 7 times 6 factorial, right? That's still expressing the same value because here's 6 factorial still has 6 times 5 times 4 times 3 times 2. Okay, so we're going to use that with the denominator over here, n plus 1 factorial. That's n plus 1 times n factorial. That way, we're going to have cross cancellation happening in the next step. Okay, because in the numerator we have an e to the nth power, and in the denominator we have an e to the nth power. We have an x to the nth power in the numerator, and x to the nth in the denominator. We have n factorial in the denominator, n factorial in the numerator. Those all cross cancel, so life's looking good right now. We got things simplified quite a bit. We're still trying to evaluate that limit as n goes to infinity. So right now in the numerator we have e to the first power times x over n plus 1. Now x could be any real number, but it's actually not going to matter, because if we're dividing it by n plus 1 as n goes to infinity, this is the same thing as what we were seeing at the very beginning with that simple series. Remember, we said this converges because as n goes to infinity, you're adding smaller and smaller terms. Same thing here. As n goes to infinity, e times x could be a billion, but n is still going to be eventually larger because we're evaluating the limit as n goes to infinity. So eventually, this is guaranteed to be this is guaranteed to eventually approach 0, right? So we know that this is definitely less than 1, as we said was a criteria of the ratio test. Okay, r has to be less than 1 to say that it converges. And that's it. So the ratio test, sometimes, when we have a variable for x and we're evaluating the limit as n goes to infinity, sometimes we can solve for x to figure out where the limit is going to be less than 1. But because we have n in the denominator, we know that the limit as n goes to infinity, this is going to approach 0. Okay, so we're guaranteed that this is going to converge no matter what x is.